Today I want to shift gears and start talking about reflection. We've looked at lenses over the last few days, and then we've looked at refraction and total internal reflection for a few days preceding lenses. The bottom line is we've talking about refraction at some level over the last week or so. Today, again, I want to shift gears and talk about reflection. There is a very simple law that we already know at some level that describes the interaction when light or any wave strikes a boundary. And that law is called the law of reflection. It says the angle of incidence as measured from the normal line is equal to the angle of reflection as measured from the normal line. Just like we have to measure the angle of incidence and the angle of refraction from the normal line, we measure the angle of incidence and angle of reflection from the normal line as well. Listen, we know this, right? If you've ever played pool, you know that if you want to bank a ball off of the bumper of the pool table, then you know that you got to hit it at a certain angle that corresponds to the angle that you want it to bump off of. Right? The angle of incidence equals the angle of reflection. Now, this law manifests itself in a number of places. The simplest place that it would manifest itself is in a question like we see up here. Okay, question number one, we have an angle of 48 degrees as measured from the normal line. We want to know where it reflects off. Okay, probably the easiest question you'll see in physics 30. It's going to reflect off at 48 degrees. The angle of incidence equals 48. The angle of reflection equals 48. Second question, a little bit harder. We know that it's going to reflect off of the first surface here. Let's assume that's a 90-degree angle to the second surface. We want to know what angle it reflects off of the second surface at. So let's draw this one out. We know that it reflects off of the first one at 55 degrees. Okay, the same angle as it strikes the first one at. But then it's going to reflect off of the second one like this. What's this angle right here? Well, if that's 55 degrees, then this angle right here is 90 degrees. Then this angle right here has got to be 35 degrees. Right? All the angles inside a triangle have to add up to give me 180 degrees. So 55 plus 90 plus 35 degrees give me 180 degrees. That means this angle right here, that's the question mark, the angle of reflection off of the second mirror, is also going to be 35 degrees. The key in this one was simply figuring out what the angle of incidence was in the second ray. And if we know the angle of incidence is 35, then we know the angle of reflection is going to be 35 as well. All right, take a look at the next diagram. This one's a little bit more challenging, but still it follows the basic rule that says the angle of incidence equals the angle of reflection. Let's assume that this is a flat mirror. You go into the bathroom in the morning, okay, after you wake up, you check your hair, you brush your teeth, you look into the flat mirror, and you see yourself, right? You see yourself in that mirror. You look pretty much the same as you really are, which may or may not be a good thing for you. How could we predict the characteristics of that image, just like we predicted characteristics of the image in a curved lens? Well, this arrow is going to represent you. This is the object. We're going to draw 4 rays coming from this object that are relatively straightforward. We're going to say that the first ray coming from this object is coming from the top of the object, and it's going to strike the mirror straight on. Where's it going to reflect? Straight back, right? If it hits it at 0 degrees, and that is 0 degrees, not 90, okay, it hits it at 0 degrees, then it's going to reflect straight back at 0 degrees. Let's extend that reflected ray back here as a dotted line. Okay, there you go. Now, let's draw another one coming off of the object. It doesn't really matter what angle we draw it coming down at. Just draw it coming down at some angle. Just make sure that when you have it reflected, it reflects back at the same angle. So the angle of incidence will equal the angle of reflection there. Let's extend that reflected ray back. And they intersect about right there. So if the top of the object started right here, then the top of the image will be right here. But we don't have a principal axis like we had with our curved lenses. So we have to draw a couple more rays. The next ray is going to come down here from the bottom of the object at 0 degrees. It's going to reflect back at 0 degrees. Let's extend the reflected ray. The next ray, we're going to draw at some angle. It doesn't matter which angle, just pick one. From the bottom of the object, we just have to make sure that it reflects at the same angle. Let's extend it back. And when we do, the two rays intersect over there. So where the dotted blue lines come together, that's the top of the image. Where the two red lines, green lines, if I was colorblind, I might say it's red. The two green lines come together, that's where the bottom of the image is. If we join the bottom of the image to the top of the image, we get an image that looks like this. What would the characteristics of this image be based on how we determined characteristics for those curved lenses last week? Number one, it would be larger, smaller, same size. Same size. When you look in a mirror in the morning, you don't look bigger or smaller, right? You look like you're the same size. Is it right side up or upside down? It's right side up. It's upright. And is it real or virtual? How do you know it's virtual? Good. It's dotted lines that intersect. It's a virtual image. And of course, you know that, right? You get up in the morning, you look in the mirror, you know that you're not projecting the image of yourself onto a screen, and you can't. You have to physically look into the mirror in order to see it. So it's a virtual image. It's same size, it's right side up, and it's virtual. Now, there's a lot of lines going everywhere there. Hey, don't try to memorize those lines. Just think logically about what's going on there. We've drawn two lines, two rays of light coming from the top, two rays of light coming from the bottom. One of the rays of light from each, the top and the bottom, is easy. Strikes at 0 degrees, bounces straight back. The second one, oh, we got to pick an angle. It doesn't matter what angle we pick. We just know that it reflects off at the same angle. And then we extend the reflected rays and join them together. And this is what we get. So if you had a much bigger angle right here or a much bigger angle right here, you get the same characteristics. Your image would end up looking exactly the same as long as you made theta 1 equal to theta 2. Your angle of incidence equal to the angle of reflection. Now, what do we see if the mirrors are curved? Okay, this is going to go back to drawing similarities, drawing parallels with curved lenses, although the images won't be exactly the same. You know that when you look into a lens, you see an image that's produced by refraction. When you look into a mirror, you see an image that's produced by reflection. The first type of lens is called a converging or concave lens. Now, think about what that says, okay, compared to when we did curved lenses. The first type of lens that we looked at was a convex or converging lens. So it's opposite, right? If you have a lens that's thicker in the middle, it's converging. If you have a mirror that's thicker in the middle, then it's diverging. Does that make sense? A converging mirror is concave. A converging lens would be convex. A diverging mirror would be convex. A diverging lens would be concave. So be careful of the difference there. I like to use the terms converging and diverging as opposed to convex and concave because I think it allows us to remember the conventions easier, when something should be positive or when something should be negative. But be prepared to see it labeled concave and convex. Just in your mind, think, okay? If I have a concave lens, it's diverging. If I have a concave mirror, it's converging. Now, see the picture there of a guy looking into a converging mirror. Clearly, his image is much bigger there, much bigger. It's right side up. Now, that doesn't mean that it's always going to be right side up and bigger. If he moves further away from this mirror, that's not the case at all. The image characteristics change quite dramatically. If you look at a diverging mirror, you guys have seen these diverging mirrors all over the place, right? I told you I told you that my son was in the children's hospital a couple of weeks ago during spring break for his jaw. He had broken his jaw. These are all over the place in the children's hospital. In fact, a couple of times I almost stopped and took photos of them, but I thought it would look kind of odd to be taking photos of mirrors in hospitals, so I didn't. They're all over the place because people in hospitals, there's always hospital beds going all over the place and equipment going all over the place and people coming out of elevators and people coming around corners. And we use convex or diverging mirrors a lot to see around corners, to see lots, right? Um, where else have we seen diverging mirrors? We used to see them in convenience stores, so the store clerk could see the entire store. The downside to it is, the upside is you can see more. You can see around corners, you can see more area. The downside is the image you can see here is always going to be smaller, right? I don't know how many of you guys have driven across the high level bridge in Edmonton. How many of you guys know what I'm talking about? The high level bridge in Edmonton, that big, narrow, really, really high, really, really narrow bridge across the river in Edmonton. Okay, yeah. You can come at it. There's like the support for the bridge that's right here, and you can come at it from this side and from this side. And there's two lanes that go across the bridge, but they're really, really narrow. So over here, they have a convex or diverging mirror. So that as you're coming around the corner, you can see if anybody's coming from this direction. Because a lot of times what happens is you're driving here, you kind of go into the other lane by mistake because it's so narrow. You want to be able to see kind of around the corner to see if anybody's coming. Again, the downside is that the image is smaller, but at least you can see more. Where else have you seen one of those diverging mirrors? Oh, okay. Yeah, that's a good point, actually. I've never actually noticed that on a golf course, but I could see that. Okay, if you've got a dog leg or you might have something like that so you can see if there's anybody on the green up there, perhaps. Because you obviously, if it's a fairly short hole, you don't want to be hitting and somebody on the green. Sure. Okay. I've seen this as well at the pool in Okotoks, the hot tub in the pool in Okotoks. That's so the lifeguards can see the entire hot tub at once. Again, the upside is the lifeguards can see the whole pool, the whole hot tub. The downside is everything's smaller, right? So it's a trade-off, right? Yep. Yeah, good one. That's a great example, actually. The passenger side mirror in your car. What does it say on the passenger side mirror of the car? What does it always say? Object in mirror is closer than it appears. Okay, why is it closer than it appears? Well, because it's a slightly convex or slightly diverging mirror, okay, which makes everything a little bit smaller and therefore makes it look further away. Why do they do that in your car? Why would they make things smaller? Yeah, bigger range, right? When you're passing somebody and you're pulling in to pass, you don't want to see just directly behind you and see this really big thing in your mirror. You want to be able to see a bigger range. The downside to it is you do lose a little bit of perspective as to size, but you gain the perspective as to a broader area. Okay. I used to drive when I was 16. I got a job delivering dry cleaning for, and I had to drive this dry cleaning van with a delivery van with no windows in the back. So I was 16 years old. I just learned to drive, and here I am driving this van with no windows. I can't see behind me except the side mirrors. And the van that I usually drove, okay, the regular van that I would drive, loved that van. Um, I learned to parallel park really, really well when I was 16 years old. Like just using mirrors, it was like I became a much better driver because of that job. But then every once in a while, it was in the shop. That van had to be, just for maintenance or whatever. And the spare van, the backup van, for whatever reason, I still don't know why. It's the only vehicle I've ever seen this in, had plain flat mirrors, plain flat mirror on the passenger side. So it never had that little sign that said object in mirror is closer than it appears. It was insanely hard to parallel park, because you didn't have that perspective with the convex or diverging mirror. It was also hard to pass, because even though you got a perfect perception of how far ahead you were of somebody, like you had to be in exactly the right spot to just see the person that you were trying to pass. in that right side mirror. All right, so we can see that we do get clearly different characteristics in different situations here. Now we want to spend a few minutes drawing some ray diagrams to predict all of the possibilities, all 10 of the possibilities. And what you see up on the board here right now is a converging or concave mirror. It's thinner in the middle than it is at the edges. Now, your template looks a little bit different than this. Okay, that's okay. Bottom line is you can see that if we draw our object on the left-hand side, it's going to be thinner in the middle than it is at the edges. You should use a ruler to draw these ray diagrams. I'm just going to sketch them just to save a little bit of time here, but you should use a ruler. This is the focal length of a converging mirror. This is 2f, or twice the focal length of the converging mirror, but I'm going to also label that C. That would be the center of curvature of the mirror. So if we made the mirror a complete circle here, that would be the middle. In other words, 2f, or the center of curvature, would be the radius of the mirror. Does that make sense? The focal length of the mirror would be half the radius of the mirror, or 1/4 of the diameter of the mirror. All right, we're going to put our first object way out here beyond 2f. So DO will be greater than 2f. Now there are 3 rays that we can draw for mirrors. We're only going to ever draw 2 for a particular ray diagram, but it's a little bit trickier here than it was for lenses because the 2 that we have to draw actually change depending upon which diagram we're drawing. Sam?
Is 2f always?
Yes, 2f is always C, the center of curvature, and we can put in brackets as well, R, because it always corresponds to the radius of curvature of the mirror. I'll probably continue to write it down and draw it as 2f, but just remember that it corresponds to the center of the circle and it corresponds to the radius of the circle. All right, so we're going to draw our first ray here. It's going to be parallel from the top of the object, parallel to the principal axis. Where do you think it's going to go from there? Where do you think it's going to? Good. It's going to reflect down through the focal point. All rays in a converging mirror will reflect through the focal point. Not refract, but reflect through the focal point. Now, the second one is not going to go down through the optical center because there is no optical center of mirrors. The second one is going to go down from the top of the object down through the focal point, and it's going to reflect right here, parallel to the principal axis. So we've got parallel through the focal point, then we go focal point, parallel. Now, where do they converge? Right here. The characteristics of this image would be larger, smaller, same size. Smaller. Upright or inverted? Inverted. And is it real or virtual? It's real because solid lines intersect. That means if we put a screen at this spot right there, we would see the image projected onto that screen. It's a little bit harder to do it with mirrors than it is with lenses, okay? But you would see the same thing. A real, inverted, smaller image projected onto that screen. You can see clearly when you look at this, the image characteristics are dramatically different than the image characteristics right here. So it does depend upon where the object is, what image we're going to get, right? The object in this ray diagram is beyond twice the focal length. It's quite a distance away from the mirror. The object right here, the guy looking into this big mirror, is really, really close to the mirror, right? So we get completely different image characteristics there. All right, my next one is going to have my object at 2f, or at the center of curvature, or the radius of the circle here. And the first ray that we draw here, just wait till I'm done drawing this again here. First ray is going to go parallel to the principal axis, down through the focal point. Where's the second one going to go? Down through the focal point. And it's going to go parallel to the principal axis like this. You should find that where they converge is directly below where the object was, directly below 2F. And the image characteristics should be same size. It should be inverted. And it should be, David, do you know this one? Real or virtual? It's going to be real. Yeah, it's going to be real because solid lines are intersecting, all right? Which means that we could project this onto a screen. Not sure why we'd want to project an image onto a screen that was exactly the same size and upside down, but we could if we wanted to. We could also look into the mirror to see it, right? If I was standing over here, looking into it, I could still see the image in the mirror. I just don't need to look into the mirror to see it. I can project that onto the screen if I want to. Yeah, good point. This is, I'm going to label this. This is DO is equal to 2F, or we could say it's DO is equal to the center of curvature, or R. Next one, we're going to draw our object in between F and 2F. So we're going to say DO is greater than F, but it's smaller than 2F. First ray is going to go from the top of the object parallel and then down through the focal point. Second ray is going to go down through the focal point and then parallel. And what do we find? Well, the image characteristics are it's larger, it's inverted, and it is real. Again, solid lines intersect, so we could project that onto a screen if we wanted to. We could also stand over here and look at it, but we just don't need to do that. Next one's a little bit different. This time we have our object at F. So DO is equal to the focal length. First ray is going to go from the top of the object. Here, let me draw this with a little bit better lines here. First ray is top of the object parallel to the principal axis. The second ray will not go through the focal point. So we go parallel through the focal point, and until now we've gone focal point parallel. This time we have to draw our third ray. Our first ray parallel through the focal point, second ray through the focal point parallel. This time we can't do that one, the second ray, because we're already at the focal point. This time we draw a ray up away from 2F. So we draw it as if it's going away from 2F right here. Right? This is 2F over here. You can see that it's drawn from the top of the object away from 2F. And it's going to reflect back upon itself. It's going to reflect straight back upon itself. Hits the mirror, goes straight back where it came from. Now those two rays don't intersect, so we're going to extend them. And when we do, we find they still don't intersect. So what do we find about this? There is no image. So first ray is as it was before, parallel, then down through the focal point. Second ray is up away from the center of curvature, or 2F, and it reflects straight back upon itself. And they don't intersect anywhere, so there is no image. In our last ray diagram, this is when DO is less than the focal length, I should say. First ray is going to go parallel, then down through the focal point. Second ray, once again, is actually going to be the third ray, which is going to go from the top of the object as if it's going away from 2F, and it reflects back upon itself through 2F. Like this. They don't intersect on the left side, but if we extend the reflected ray and we extend this reflected ray, then we find they intersect over here. So once again, it's the first ray and the third ray, not the first ray and the second ray. We find that the characteristics of this image, it's larger, it's upright, and it's virtual because dotted lines are intersecting. In order to see this one, we'd have to physically stand over here and look into the mirror in order to see it. Now, let's go back here Let's go back to these ray diagrams just for a second again. Okay, I know you've already drawn them here, but I don't know if any of you guys noticed the pattern here or not. If you had a convex lens, which is converging, okay, we have a converging or concave mirror, both converging here, the image characteristics ends up being the same. If we had an object distance beyond 2f for a converging lens, these are the characteristics that it produced. If we had an object that was at 2f for a converging lens, these are the characteristics. If we have an object that's between f and 2f for a lens, these are the characteristics. If we had an object that was at f for a converging lens, there was no image. And if we had an object that was smaller than f for a converging lens, these are the characteristics. Some of you will choose to draw ray diagrams. Some of you, because the characteristics are the same for converging, whether it's lens or mirror, will remember the characteristics, will choose to remember the characteristics, and that's fine. Okay, because there's 20 different ray diagrams we draw, it sounds like it's a lot to remember, but it's actually not that much. Because when you look at the converging lens versus converging mirror, they produce the exact same characteristics. Now, when we flip forward to the diverging mirror, where this is going to be F and 2F, or center of curvature and R, once again, just like for diverging lenses, we always get the same characteristic. First ray, parallel, and then it reflects away from the focal point. The second ray is going to be drawn towards the focal point, but it can't make it to the focal point because there's a mirror in the way. And then it reflects back upon itself. We'll extend that one, the reflected ray, backwards. And we're going to find the characteristics of this image. It's smaller. It's upright. And it's virtual. I'm going to ask you to draw the remaining 4 ray diagrams for at home tonight. You're going to find that just like with diverging lenses, they all produce the same characteristics: smaller, virtual, and upright. So again, if you think about converging lenses, same characteristics as converging mirrors. Diverging lenses, same characteristics as diverging mirrors. So here's your homework for tonight, guys. Remember, you got a quiz tomorrow. It's quiz number 23. And of course, you've also got the remaining 4 ray diagrams for this. And that's it.